Thank you, Kai-Ming, for the introduction. Yes, yeah, on behalf of the team, I'm more than happy to give an overview of our project work over those years from later 2016 to this year. And so basically the project is completed is already, and I'm happy to report some of our activities, research, and achievement. Again, it's got a long title, not that long, but the focus is, topic is wastewater treatment. But the focus is not really wastewater treatment. It's basically two sides of the effort. It's water pollution control and the resources recovery. And our main focus is resources recovery. Let's start from here, a very brief background after Professor Gan about water pollution. Start this from this statement. My team member, Professor Xiangdong Li, gave me this statement. So water is the most vital resource on Earth. We started this applications from this statement. Now I use this for my teaching. So it's very important because water suffer problems like water shortage and water pollution worsen the shortage problem. And water pollution in China is a big problem. In Hong Kong it's better, but not much better. Still have a problem to solve. So that's a big background. And talking about the water pollution, there is an effort for water pollution control. So in our field, basically it's wastewater treatment. Each person in Hong Kong, other places a similar situation. So people use water, produce or discharge wastewater. So every single person in this room discharge like 200 liters, 300 liters. It's a lot of water, wastewater. Someone got to do that, to clean up, to protect the environment. So for this effort, water pollution control, so look at this. So this is in Hong Kong. In Hong Kong, it discharges a huge amount of wastewater. So it's not just a one-time thing. It keep coming. Today, tomorrow is 2 million cubic meter wastewater. So current treatment is one treatment methods, and what we try to treat, to remove, to clean up. So basically, it's for the removal of nutrients. Yeah, from early talk, we learned the nutrients. Nutrients cause a problem, nitrogen, phosphorus in particular, and organics. Those are dirty things. So they are in wastewater, need to be cleaned up, to be removed from wastewater to produce purified water or treated water for discharge. And emerging organic pollutants, we didn't really pay attention to those pollutants 20 years ago, like EDC. Now there's a focus of the research in recent years because it caused long-term impact on the environment, ecological system. And for those kind of purpose, so wastewater treatment is difficult and costly because we are talking about the low concentration. I didn't have like this. 400 milligram per liter means milligram per liter is a ppm, so it's one molecule in 1 million molecules. Those need to be removed to that level, so it's difficult. So from, for example, 400 down to 40. So 30 molecules in 1 million water molecules. That need to be removed. So talking about the removal is not difficult, but the removal to that level is difficult and costly. And in Hong Kong, this is a Hong Kong situation. So the space is always a problem. That's why the innovative treatment technology is needed. Because specifically in Hong Kong, CEPT, okay, CEPT is here. That's the technology used here. It's not a full package of treatment. It's still primary. It's still primary treatment, so that need to be upgraded, and need space-saving technologies are also Okay, it's done one thing, it's get something done is one thing, but also at a cost-effective manner, that's another requirement. It's more difficult to achieve. Okay, more specifically, well, as I mentioned, someone got to do it. When we are doing it, wastewater treatment is already done to different levels. It's already there. But you look at the problem. In old days, it can be okay. In countryside, it can be okay. But in a concentrated urban area, a lot of wastewater, the huge loading, great input. So the sustainability matters at this point. You look at, engineers, if you look at the material flow, mass balance and the material flow, we follow the carbon flux. So 7 million people discharge wastewater containing organics and nutrients that need to be removed. Okay, that's the starting point of the story. Talking about the current wastewater treatment, so the major effort or so-called achievement is degradation and oxidation. You know dirty things are there, organic, as I mentioned, organics. So how to remove it? Oxidize with carbon dioxide. So that's the approach, which is okay for that purpose, but you know carbon is no longer a good term in nowadays. It's greenhouse gas is one of the major concern in nowadays. Okay, this is one side of a problem. And for wastewater treatment, we know carbon dioxide, but not everyone really understands this problem, but from this illustration, you get the idea. So some are concentrated into sludge. I mean, some are dirty things, concentrated sludge. Huge amount of sludge is produced in the urban environment. Like in Hong Kong, more than 1,000 tons per day. 1,000 tons of those dirty things produced. So how to deal with this? It's no good way to deal with it. It's always, it's the most expensive and challenging task, a burden to the urban environment, urban government. So talking about the treatment is incineration, landfilling, or illegal discharge, those are that. People don't want to really touch the problem. So current practice is like this. It's a conversion of a problem from one problem to other problems, like this carbon dioxide emission and the sludge problem, sludge generation problem. So that's the description of the problems. With this project, okay, what we want to do, that's back to 7 or 8 years ago. We formulated a team, discussed the situation, and we look at the problem. We want to develop a new approach. So the so-called new, excuse me. Yeah, I don't have other problem, just an allergy, okay? It's really allergy. Don't worry. My family doesn't worry about this. So our approach is this. So we're still doing wastewater treatment. Someone got to do it. We are doing it. But the approach is not carbon oxidation, organic oxidation, not the sludge production. It's resources recovery. Resources recovery. You look at the terms organics. We're eating organics. Organics must be a good thing. Organic good things. Nutrients, fertilizers. Those are good things. You waste it. Translate to other problems to the environment. So why not recover it? You still separate, still remove, but concentrate in a good way and convert to value-added product. So in terms of purpose approach, okay, this kind of, we say is attractive, promising approach. So what we want to achieve with this project, okay, we did it early. Now almost all those many people in this field talk about resources recovery, this or that, but somehow we brought up this term a little bit early, and we have the good support of this theme-based project. So this is the purpose. This is the focus supposed to be achieved with this project. The resources recovery and the conversion of those waste to value-added product. Okay, that's a project summary. I shouldn't really waste a lot of time on this. It's a teamwork, team effort, a big team. It's from, all the members are here. We will have a happy time, good time working on this important project, important problems, and come out with a few good solutions. From my description, you understand it's not a single problem. It's not a focused issue. It's really need integration. It's sharing, distribution of the task, and the integration of the effort and the outputs. So basically, the project was developed and divided into a few research programs. There are program leaders taking care of each research program together with the tasks. And you're working on this, you know RGC. RGC has a very close monitoring of the project progress. So this is not my table. It's the table designed by RGC. So we follow this. So there's objectives, research programs, and the research tasks, and the stage from 1 to 6. So that's basically we are right here. So project really completed in good term. Then, okay, we want to convert waste into resources, valuable product. So how to do it? Okay, so what product? People would ask this naturally. Sludge. Follow my early slides. We want to convert waste organic to organic acid. Organic acid. Go one step further would be PHA or bioplastics. So it's organic to organic, dirty organic to good organic. And ethanol. Ethanol is another product, energy product. And the biofibers. How to get biofibers, I try to cover that later. And the fertilizers, phosphate and ammonia, nitrogen. So those products we aim at the very beginning or during the project course. Okay, getting to the technical part. So this, I start from here. Traditional, so-called conventional wastewater treatment. So primary separation, produce sludge, then biological treatment. Biological treatment is a major components of wastewater treatment. So within this stage, 8 hours to 16 hours, organics oxidized, nitrogen is converted to nitrogen gas, and the phosphate is fixed into sludge. So all those so-called major pollutants are oxidized or discharged, wasted, then get purified water. This part is good. We are happy with this. But look at the waste. You look at the resources or material, really the waste. So what we are doing, so number one is intention, actually, is minimum change. Minimum change. It's easy, sitting here to propose a new approach. So wastewater with treatment should be done in this way or that way, but that's not practical because we already have $1 billion infrastructure established. It's already built up. It's in operation. That's supposed to be operated for the next 30 to 50 years. So that should be utilized. So that's the constraints. Our intention. So it's supposed to be minimum change. So you look at this. So we still follow this, the treatment scheme. But at this point, we replace this conventional sedimentation with membrane filtration, ceramic membrane filtration. So separation was okay. Primary sedimentation. In Hong Kong, we use chemically enhanced sedimentation. Still good, it's better than this. And one step further, the utilization of new material, ceramic membrane for separation. So we don't want to oxidize organics, oxidized material you want to separate and convert it to sludge and perform recovery. So that's the whole package, 1, 2, 3 focus of the research program, as you may recall. So chemically enhanced membrane filtration to get the sludge and the concentrated pollutants. Okay, pollutant is the bad term, but in our view, those are the precursor of resources. Then side stream acidogenic fermentation. As I mentioned, we convert organic to organic acid. That's from this statement, you would agree that's a simple conversion. It can be done without much effort. Because you leave organic there, it's turned to organic acid anyway. It's like that. But if not sufficiently concentrated, it takes a long time, and the conversion efficiency is low. But with this kind of concentration, this step is almost automatic. Low cost, that is important. And with this separation, phosphate can be recovered. Of course, precipitate phosphate, and is concentrated here. And connected, okay, because phosphate, as I mentioned here with precipitation, phosphate is settled here, become part of sludge. So how to recover? Well, remember I mentioned this acidogenic film fermentation. pH is low, then phosphate resolve into the liquid phase for recovery, fertilizer recovery. Then the third part, okay, this part is a kind of new approach. We really want to push forward a little bit this. Then we brought up this, we proposed this. It's really what we proposed in early years. Thermal hydrolysis. So you look at the sludge treatment, as I mentioned, incineration. So to burn everything into carbon dioxide. So that is fine. But everything to carbon dioxide. We don't want to say that, but still want to get the organic. We use the thermal treatment, but the thermal hydrolysis really dissolve the organic from the dirty organic to the clean organic, become organic solution. Then we apply fermentation. Where is the fermentation? Yeah, sorry. Fermentation, fungal fermentation. We grow fungi, and the fungal biomass is already a product. That is the intention here. Sometimes to get the byproduct, like ethanol. So that's the whole scheme of this research. Let me quickly give you an outline of those so-called innovation on the focus of the programs one by one. So the first one is chemically enhanced separation. So this is our new scheme. People would argue, okay, so this is a conventional treatment. Then you build this. At one point I said we want to do minimum change, then build more facilities. Different, it's very different. Because this flow is like 100, if I use the number 100. So this flow is 1. So 1% of this flow. So those are very small units, relatively, very small unit. Because we are talking about sludge, concentrated material flow for sludge refinery. That's in the title of the project. Then convert this material to different products. So those are the small facilities. Those is established existing infrastructure, urban infrastructure with water treatment facilities. Those are going to be fully utilized, and we add this for recovery. Okay, so the idea is illustrated here, and for the so-called enhanced separation. Use a ceramic membrane. So this is kind of new product. New product in comparison with this, those type of conventional ceramic filter. Those are expensive, and the new is a flat sheet ceramic membrane. The cost is like 10%, 20% of this, become available and affordable. So now it's become quite popular in our field. I mean, water purification, wastewater treatment. And with this kind of material development, the make it possible, make a big difference. Utilization of this new filtration means in conventional treatment like this, the whole separation takes 2 hours. With this new separation, less than 15 minutes, within less than 15 minutes, it's already done. And the separation result is amazing. So this is dirty water to start with. After 15 minutes, we get this. It's already most of, we are joking around, it's 80 to 90% of wastewater treatment work already done by just one step, 10 minutes filtration, because really thanks to this new material, filtration flat sheet ceramic membrane. And this is so easy to be used for upgrading of conventional or existing wastewater treatment facilities. So what is existing wastewater treatment facilities? So basically tanks, water tanks, empty tanks, big tanks, and this can be easily installed into tanks to upgrade the conventional sedimentation tank to this, to filtration. Okay, very happy to see that result. It really worked out. And okay, so they have this ceramic membrane, and we use it for our treatment. So what is our contribution? Well, things are not that easy. You really put the ceramic membrane into our treatment facilities, as I mentioned, the wastewater tank. It didn't work. It didn't work because of membrane fouling. Okay, they are designed for clean water production or water reuse, not for wastewater treatment at a very early point. So it didn't work. You look at this. This is a fouling, indication of a fouling. It's basically pressure increase. For filtration, you need suction, right? You need to press water through the filter. So the pressure increase like this. Less than 1 hour, the whole thing is basically blocked. It didn't work. The idea is good. Wishful thinking is good. It didn't work. Okay. Now what we did, that's our expertise. We do the flocculation, coagulation, flocculation, so basically chemical enhanced separation. So with a little bit of dosing, it's really little chemical dosing. Those are not expensive chemicals. Iron or aluminum, we call it coagulant or flocculant, a little dosing. You see the extension. So without this pre-treatment, so the filtration basically failed in 20 minutes. 20 minutes. Yeah. Just like the student told me it didn't work. I said, how it didn't work? It's supposed to work, but it really failed in 20 minutes. But with this flocculation, and we call it the precondition of flocculation, the duration time can be extended to 20-some hours. 20-some hours is good. This is kind of early result because the work already published. I really update this. So the later follow-up work, we can extend the filtration to 3 days, 70-some hours. 70-some hours, then you do the cleaning, then 7-some hours, 3 days, do a little bit of cleaning. Cleaning is easy, it's back washing. It's not really, washing machine, this type of cleaning. So it's just back washing, the membrane is recovered and ready for next cycle of filtration. So with that, we made a big difference. So make it workable for wastewater treatment, really for the very first time for this kind of utilization. And another related, I don't really talk about removal of conventional pollutants. It's, we are happy to see the filtration. The result is good. It certainly works. But even for this EDC, got the long term and a lot of attention in the scientific community and even public. Out of public, there are attention on those. So with this chemical flocculation, I mentioned that. So basically it's a grab, really attach those pollutants, different pollutants. In old days, our focus, again, particulate matters, organic, non-dissolved organic. Now, so our team member, Professor Kenny Liang found, is also attract capture EDC into the sludge. So all those separation is good. We are happy to say that because this is a simple, in terms of treatment, 5 or 10 minutes of flocculation is simple treatment, but the big difference. So those are the results. So the research really track the removal of not organics, but those chemicals. There's a different type of chemicals, and the removal result is better than expected. So again, happy to report this part of a study. And the second one, acidogenesis, fermentation. Those are dirty wastewater. You saw my photo. So dirty wastewater, after a layer of filtration, 20 minutes later, purified water is produced. So where goes the pollutants? It's here, 100 times concentration. That's really what we want to achieve. 100 times concentration, got concentrated organics. Then the following part is easy. It's fermentation. You get a long-term acidogenic fermentation, actually doing nothing, just leave things there for 2 or 3 days. It's converted to organic acid, volatile fatty acid, organic acid. Those dissolved organic acid can be easily separated. Again, membrane filtration get this, and additional is cost added conversion is this. VFA is already good. It's already one of product can be used for different applications. But to make a high sounding story, so we convert VFA to PHA. PHA is this thing. PHA is bioplastics. So nowadays, this is a very attractive product. And the good thing is it's really waste to product. And this is biodegradable organics. So the recovered product, including VFA, can be utilized for different purposes. Quickly, I'm going to show one application, and also this PHA production is attractive because the usage of plastic is not really encouraged, and the bioplastics is going to be more and more popular, going to be encouraged, and this is really working in that direction, convert waste to biodegradable organics. And for fermentation, and the team did research on the fermentation. On the fermentation, excuse me. For sludge fermentation, and actually we go one step further. Look at the urban waste. Sludge is one headache. One sludge gives us a headache. And another one, food waste, is a food waste. So this is really facilitated by the government. EPD is promoting this co-fermentation. Term, where is the term? Okay, here, co-fermentation. You saw the term of co-fermentation is the solution for 2 problems, the sludge fermentation problem and the food waste treatment problem. We combine these 2, it's going to create some difference. Actually, also bring about really good benefit. So the research team work on this co-fermentation versus a single fermentation and track this whole biocommunity change in relation to the fermentation performance. The so-called performance, 2 things we are looking for. Number 1, production of organic acid. So organic to organic. Number two, with this fermentation, as with the acidogenesis and the pH drop, phosphate release. So phosphate is released, and that's ready for recovery. The two things. Again, on this fermentation. Don't say fermentation is old technology. Of course, we like engineers like old technology, reliable. But we also do innovation. So innovated technology, but step after step, step by step. For this one, the small step is the utilization, the use of electricity for fermentation. So electricity facilitated or enhanced fermentation. And fermentation is still going to happen, but the additional benefit is the separation. After fermentation, everything is still in the pot. We know the good thing here or there, but how to get the product is a demanding work. At one point, I mentioned use membrane filtration to get organic acid. That part is good, but how about the others? Phosphate, okay, there phosphate inside. How to get the phosphate? That's more difficult, more demanding. This electricity, actually, this setup really help in that regard. With in different chambers, with an anode and the cathode, and the product can be separated. Ammonia is separated, iron is separated, phosphate is separated, organic acid is separated. Because in different chambers, in different forms, different chambers, that's already separated. Different forms means some dissolved, some precipitated. So just good separation. One internal usage of the product, one example, we actually already adopted in practice, is use of organic acid. Where is the carbon source? Use VFA. Earlier I showed this term, this thing is useful. Even inside the treatment works is for nitrogen removal, denitrification. This provides the carbon source for denitrification. So means in our field, so on one hand we do wastewater treatment, remove organics. I keep mentioning organics, it's pollutants. But for nitrogen removal, they also need a good carbon source for denitrification. Somehow that's part of nature. You have to go through this direction. Then the treatment works has to buy the organics, buy organic acid or sugar, those type of organics as a carbon source for denitrification. So certainly that's not really not an environmental friendly or sustainable approach. So this kind of conversion, organic converted to organic acid, which provide carbon source for denitrification. So that is another utilization. The third one I like to highlight is this sludge refinery. Okay, the first two is a little bit conventional, just one step further. This is a big step forward to really convert sludge, because sludge is dirty things, is the mixture of all those pollutants, difficult to deal with. But we want to carry out a refinery. We like the term refinery. With the term of refinery, we're going to convert something to the more useful things. Thermal hydrolysis, got the organic solution, then carry out biosynthesis to produce something. See, what is supposed to be produced? One example is this. This is a sludge. It's really, difficult to do anything with this. After hydrolysis, we get this. And the remaining sludge with low organic contents, much more stabilized, easy to be dewatered. That part is good. And the liquid this liquid is organic over 10,000 concentrated organics, and we use this as a feed. Also, after thermal hydrolysis, totally disinfected, sterilized. There's no microorganisms. So you put something in there, I mean microorganisms, you put there, they grow. So in this study, we do fungal fermentation, put the fungi species in there. And those fungals produce, we call it hyphae. Hyphae means fiber things. And why hybrid things? Okay, like this, that's the product. They grow to a certain concentration, and we capture this and dry it and produce, it's like a paper-like product. So amazingly, so with this thermal hydrolysis and fungal fermentation, we convert this thing to paper. We call it a fabulous product. And of course, it can be paper or can be packing material, so basically capping material. Of course, students did more studies. They convert this to what's that? Carbon fiber, or carbon for different type of carbon electrode for battery usage. This is another long step, but here we are happy to say this. Those are workable. So hydrolysis and grow fungi species produce fiber product. After drying, we convert this product to paper or packing material. And more specifically, thermal hydrolysis. Thermal hydrolysis is sounds scary, but it's not that terrible because it's like 160 Celsius, below 180. It's already commercialized technology, not used in Hong Kong. Started at Europe and adopted in the US, Japan, and now it's quite popular in China. Because Hong Kong uses sludge incineration, as you know, so basically we already get into that direction. You're not going to do too much work for sludge utilization, already incineration, But in some other places, they want to utilize the sludge in better. Okay, I only have 3 minutes. Yeah. Okay, sorry. Terribly sorry. I only have 3 minutes. I still have half of my slides. Okay. Sorry, Camille. That's messed up. Okay. On this part. So that's fermentation, as you mentioned. This fungal hyphae, the fiber type of products is just like to making paper. You get any size, big paper, small paper, big paper, and get any thickness. That's type of a product. So quite exciting to see the result like this. And the system integration. Those are the focused, development, problem-based or innovation-based. And at the end of the day, we talk about wastewater treatment. We need to present the full package for the practice and also for this project. So that's another task of this project. So integration. As I mentioned, we have good elements here, there, filtration, conversion, this or that, need to be integrated together, and we carry out the pilot study. So that's integrated. It's no longer lab beakers and reactors. It's really need those reactors, this or that, and automatic control bioreactors, this or that, and carried out in wastewater treatment plant in Shenzhen in past 2 years. I still have a few research highlights from the members from the team on different aspects of the research. Maybe I just give a quick overview. It's already highlighted overview. So one is the phosphate recovery. Now it's a popular topic, very popular topic. So we try to close the loop of so-called circular economy or sustainable circulation. So you talk about the phosphate. Phosphate is a very valuable. Where is it? Very valuable resources. It's going to be used up. Many years ago, I never heard of that, but now I really worry about this. It's going to be used up in less than 100 years. No, I shouldn't worry about that. It's 100 years later, but it still matter. And PHA production, as I mentioned, and Professor Low did this, and WSD really interested in this technology for phosphate removal and recovery. Still on this topic, removal and recovery. Professor Shi did this to convert waste to ceramic for waste stabilization. And you heard ceramic. You may recall I mentioned the term of ceramic membrane. You look at this. So you see there is another cycle from solid waste to ceramic membrane for the utilization of water purification. It's a wonderful loop. Another innovation, the combination of filtration, so advanced filtration and catalysis. So treatment and filtration, so basically separation and degradation combined in one cell. And talking about EDC and the emerging organic pollution, emerging pollutants is all different type of pollutants. And the team did this. Professor Zhang did this and published in the top paper, but it's not really publication. Really attract the attention of this community because people consider this, so-called worry about this. We have long list of emerging pollutants, hundreds, close to approaching 1,000. So which one is more important, should be considered, should be taken care of. And he did a study and gave a priority list of these pollutants. And modeling work, water reuse, I have no time, but it's really a byproduct of this research, theme-based research project. So Hong Kong has a really unique feature for water reuse in Hong Kong because we have this seawater toilet flushing system. So the dual piping system is already there. Those are the systems talked in other countries. They don't have those set up, but Hong Kong already have this foundation infrastructure for this kind of water reuse, but not just for toilet flushing. It's going to be expanded to different usage. And global impact. And Professor Kenny Liang is carrying out this. It's a program under the UN. I heard it's like a whole country of China has one team, and Hong Kong already have one team join this for global estuarine monitoring. A lot of activities, happy time, and then affected by pandemic, but we still carry out this regular meeting, workshop, half year, and we really keep this going. And members really learn a lot from each other and good interaction, at same time stimulation and promotion, and for the delivery of a good product. And those are another key thing. And we've invited by the HKIE, published this special issue. It's not special, they call it theme issue on water pollution control and resources recovery. so one of 5 same issues in the past 20-some years. So it's happy to see this local attention on this research outputs. Another highlight is this, because this is a project and those foundations, oh, actually you're doing this, and somehow they gave us the donation. And we formulated this Center for Water Technology and Policy. At the beginning, I think we just get more money to do research, but no, we learn new things. I learned new things. It's not just the technology, and they want to add the elements of policy. And I really learned a lot about this policy because, see, this for a person like me, it's an engineering training background. We think things are simple, straightforward, right? This is good technology, is supposed to be adopted. Then you work with those. By the way, those joined by 2 faculties. One is, is my team. Another is social science. And you work with others. They have a very different thinking. It's good thinking. Good thinking is not just technology, the whole implication, the social impact, the legal thinking, and there's a policy, government. It's more complicated than technology, than research and technology. So now I'm kind of moving a little bit towards the soft side of this technology. And this research center is really for the interface between technology and policy. And at the beginning, we didn't really think of that, but somehow, those foundation people, they think in a good way. So try to bring together the 2 sides, the policy people and technology people together, and work out a good solution. I think it's quite good. Difficult to get money to work on those things, and get the donation work on this is beneficial, and also technology transfer. We have a few patents, and one attract attention, and we listened to the company for the follow-up development, and get some get some income for the university. There's upfront fee, and hopefully we get good loyalty for the continuous scientific research. That would be talking about the circular economy. That would be good, and also media attention, and it's a benefit. That's all in our report already. So again, it's not just saving, it's really about the resources recovery. And that's the early of such study in Hong Kong, in China, or globally. And we are happy to deliver all those results. And eventually, I just gave a breakdown of this early chart. So what we are thinking, okay, reduce this, reduce the sludge production, and recover different forms of organics as a product for in situ utilization or for resources recovery. That's okay. That's our vision of the research of the whole team. Otherwise, the urban environment would turn into this. Submerged in sludge. Yes, you get 1,000 tons every day, or like this. Okay, happy to say that. With that, thank you. Of course, thank all the team members.
Thank you much, Professor Li. I think your presentation addressed Professor Chen's questions. How can we be at the upstream to really reduce the pollution's release? Maybe let me have a quick questions from audience, if there's any.
Okay, so sorry for the time management.
Right,
the old team members give me material.
Well, you're working with...
That is the situation.
Questions from audience? Maybe we'll have one over there.
Thank you, Professor Li. It's still not that upstream. Okay, of this project, do you have any suggestion for the discharging policy in Hong Kong or in this area? What kind of thing can be discharged, can be found in the final sludge for your, say, like recovery refinery? Probably you have some comments, some suggestion for the source reduction.
For source reduction, actually, I don't think Hong Kong is still facing, tasks or difficulties in terms of regulation of discharge, because we don't have much industry left. And agricultural activities is minimum. So most of the wastewater, talking about Hong Kong, basically is a domestic wastewater or commercial, this type of wastewater. For those, government really not really impose much regulation because you don't really bother regular citizens that much. And the conventional usage of water and discharge wastewater is no strange chemicals or heavy metals. So it's really not much regulation on this upstream regulation. Probably you are referring like for industrial regulation. That's really the long list of regulation, this or that, because we really have a very strict regulation. That's a part of reason already, encourage the industry move from Hong Kong to China. So for that part, which is good, means there's not much industrial burden and not much agricultural requirement on wastewater treatment in Hong Kong. Yeah.
All right, thank you very much for your questions. In view of time, please allow me to invite you to thank Professor Lee again and also the questions. Thank you very much. And now we